Now that you have used WATAM to define the wave speed in a few pipes, we continue the lesson on compressive wave speed. The focus will now shift to the influence of entrained air, or entrained gas, on how fast a compressive wave travels through a pipe. It is important to note I am talking about entrained air bubbles, not dissolved air content. We are discussing the significant impact of air bubbles because bubbles act as a set of shock absorbers dispersed throughout the fluid. The concentration of air chemically dissolved into a pipe's fluid does not have this effect on compressive wave speed because dissolved air does not create a set of shock absorbers. Pages 34 and 35 in your workbook summarize the essence of Wiley and Streeter's explanation of how pipe wave speed is affected by the presence of air bubbles. This slide shows how well Wiley and Streeter's formulae relate to research experiments. Note how an extremely small percentage of air bubbles drastically reduces the pipe wave speed. Let's take a closer look at how to calculate the blue line in this slide using a spreadsheet.
Here I have opened the Air Entrained XLSX file that you will find in the Exercise 2 folder of your USB memory stick. This spreadsheet is simply an implementation of Wiley and Streeter, Kabori and Pearsall's work on developing the formulae for evaluating the wave speed in a fluid-gas bubble mixture. You can find references to their publications in your workbook. So what can we see here? Let's start with the small dark green dots. They are the values measured in a particular experiment. The user input fields in the spreadsheet are set to match the conditions that existed in the experiment. Consequently, when you look at the blue line on the graph, it is showing how closely the formulae published by Wiley and Streeter match the experimental results. The blue line includes pipe elasticity, while the small red-yellow triangles apply the formulae, ignoring pipe elasticity. What should we learn from this? The answer is that a very small air bubble content by volume in a fluid dramatically lowers the compressive wave speed. These dispersed shock absorbers dramatically lower the compressive wave speed. Okay, so let's move on to how you could use this spreadsheet if you need to. Note that there are only 9 user input fields, and they are all marked as shaded fields that look like this one. Running through them individually, you need to specify the mass density of the liquid and its bulk modulus, that is, its resistance to compression, the pipe's modulus of elasticity, its internal diameter, wall thickness and Poisson's ratio for the pipe material. Over here specify the operating head and temperature of the pipe system. And lastly, the adiabatic index of the gas in the bubbles. Remember the formula pressure times volume to the exponent of N is a constant. N is the adiabatic index. Before leaving this spreadsheet, let's develop a feel for how things may change in different pipe systems. Remembering the experiment was done with a nominal 100 mm diameter stiff, galvanized steel pipe operating at 33 meters head. What is the effect of entrained air in a bigger pipe, say 1400 millimeters? Okay, the effect is less significant at extremely low air content due to the pipe's increased flexibility. Putting things back as they were, what is the effect of system operating head increasing, say 100 meters? That result suggests that at higher pressures, it requires more air bubble content to reduce the compressive wave speed by the same amount. Simply put, there is more resistive energy stored in the shock absorbers, the bubbles, at higher pressure. We suggest you remember that this spreadsheet is available if you ever need it. However, note that JClem Consulting Proprietary Limited offers no warranty that data and formulae presented in this spreadsheet are correct or fit for specific purposes that you may wish to apply them to.
Generally, a lower wave speed improves the transient behaviour of a pipeline, so it is tempting in systems that carry wastewater to assume that a lower wave speed will occur due to the presence of entrained gas. However, in the context of engineering projects, with the goal of delivering safe designs, a number of questions are highly pertinent. When would you need to adjust pipe wave speed for gas bubble content? Will gas bubble content be present in all operating conditions? Could using a low wave speed, assuming the presence of gas bubbles, be a non-conservative design case? Is there any tangible evidence of lower wave speeds being measured in the field? How does an engineer quantify an appropriate gas bubble content by volume? For example, sewerage system effluent certainly releases hydrogen sulfide gas at open air effluent interfaces. The question remains, in a pressurized sewer pipeline, are bubbles of gas persistent in the effluent? Or is the hydrogen sulfide dissolved or otherwise chemically bound within the fluid effluent? Has any utility conducted field testing on sewer pressure mains to quantify the compressive wave speeds? If not, assuming wave speeds reduced for gas bubble content may lead to non-conservative design. Thanks for watching. Now please take a few moments to consolidate the key messages and review what you have learnt in this lesson.